Okay, since there was a glitch with the Zoom connection during the class, I'm gonna re-record this class in this form. Okay, so this is where I stopped last time. I was discussing the possibility to go beyond the context-free class of formal languages into the context-sensitive class by not enlarging too much the class of languages considered. And so among the other classes that I was discussing last time, there's this case of the multiple context-free grammars, where you can introduce things like the course-serial dependencies by having a vector of different context-free grammars, and then functions that combine these different entries of these vectors in some order, including allowing for the cross-serial dependencies. And this class has the advantage of including the context-free, but being strictly larger than the context-free, including the three adjoining grammars in some form, between the one and the two multiple context-free grammars. And they are also, it can also be shown to be equivalent to merged grammars. But as I was saying, to the computational minimalism, formulation of computational minimalism of Stapler. But there's a catch, in this equivalence, in the sense that they are formally equivalent in the sense of their generative power, but not in the sense of the computational complexity involved with that. There's a result of Berwick that shows that there's the actual merge formulation is exponentially more condensed, more succinct than the multiple context-free derivations for the same structures. And so last thing that I actually want to discuss, from this perspective of generative grammars related to coming from the perspective of formal languages, is the minimalist grammar, so stable for computational formulation of minimalism. And this I will have to return to later when I make an explicit comparison between the most recent new formulation of minimalism, which is the main topic of this class, and the previous formulations. And especially for the previous formulations, I will take the model of this formulation of stable, because it's the closest one to be formalizable in an explicit mathematical sense, and so it will give us the right ground to compare it with the newer one, which I will present from the mathematical point of view. So in this perspective, what one needs to construct this kind of minimalist grammar is, again, some finite alphabet and a certain number of labels of types of labels, which I'll whole purpose I will explain in a moment. And these are labels that allow you to do certain kind of feature checking operation that will tell you if one can apply the basic operations of the merge model, which in this older formulation were separated into merge and move, and in the newer formulation are actually unified as the action of merge. And the thing is that one of the main significant differences, as I will discuss later, between the newer formulation of minimalism and this older one, is that in the newer formulation of minimalism, you have a free, generative process, and all these conditions, that come from feature checking and so on, are imposed later as kind of filters that detect which of these freely constructed structures are viable and which are not. Whereas in the older formulation of minimalism, you have these two processes happen at the same time. So the feature checking is happening at the same time as the structure building operation that is telling you whether the structure building operation applies or not. There are actually slightly later formulations of the computational mechanism which of this computational minimalism that already are kind of trying to separate out these two operations and making this feature checking happen as a labeling algorithm later on the structures that are produced. So there's kind of intermediate in this sense between this older formulation of Stabler and the new one. And I will not actually have room for discussing those, here in the lectures, but I just, mention that these things, intermediate versions kind of exist and are maybe more directly useful to a comparison with the newer one in terms of discussing computational minimalism in the newer formalism. So here, there are two kinds of these feature labels, and there are selectors and selectees and licensors and licensees, and these respectively will take into account whether the two type of operation merge and move can be applied and where in the structure they can be applied. And so the lexical, the set of lexical items and features, contains, lexicon and these kind of which are the strings in your alphabet, and also this kind of selectee and licensor licensee symbols. And here are some concrete examples of how these things are applied in practice. You have lexical categories, they distinguish what kind of role certain lexical items are supposed to play in the sentence formation. Adjectives, adjective phrases, adverb phrases, noun phrases, verb phrases. These are the classical kind of lexical categories in linguistics. And there are functional categories like coordinate conjunction, determinant, negation, preposition, prepositional phases, and things that take into account tense and so on. And so one usually writes with this equal symbol, n plus a certain category, is something that will select for, an item that has this type of labeling, this type of X labeling to form a new structure. And the licensee is correspondingly, this minus X is what is that kind of labeling that is required to be able to force movement at that point in the structure. And the licensor feature is the one that you need to match, in order to be able to do movement like WH for WH movement or case and so on. And so in this formulation, the main operations, instead of having the production rules of the context-free grammars or these various context-sensitive cases that we have discussed, you have only two kinds of operations. You don't have to list all the different production rules. The two kinds of operations in this form, all the formulation we call merge and move, and essentially they are organized in this way. If you have two structures, one of them has a labeling that starts with this kind of F, where F is the feature that you're using to do the merge operation, and the other. So this means that this part of the structure is calling for something that carries the F label at the start of its labeling, what was complete labeling. And if you have a matching of features in this way, then you can use that feature to form a merged structure. And the feature that you have used to form the merged structure disappears from the resulting labeling. And then you just have two rules for. So there's another indication that I'll talk about in a moment, which is the signs that keep track of where the head goes, the head of your structure goes, and I'll discuss that more in a moment, and I will come back to discussing the role of heads a lot later on. So, but there's a rule for this, depending on whether this is a single lexical item or is a formed structure itself, what the head does. But otherwise, this is just the way that these features are used for forming a new structure via merge. And the other move is an operation that extracts a substructure at some node inside the already formed tree. And if that substructure carries this other kind of label that signals that movement is possible, and the overall structure has the matching movement label, then you can extract this substructure and merge it with the remaining structure on the other side. And again, the feature that is used for movement is removed from the resulting labeling, and you have a new label structure. And in this case, there's a single rule for how you assign where the head goes. So you can write that out, instead of with the pictures that I just showed, you can write that out, explicitly as a formula, what merge does and what move does. And note that, in the kind of new formulation of that I will be talking about later, this kind of description of merge and move changes quite significantly. It becomes, so here your trees are planar, which is very important to know the tree structure is and so the labels are an ordered sequence. These are the strings, the resulting strings. So you think of it in terms of formal languages. And so all the moves keep into account this planar structure of the tree, and this head also follows what goes to the left and to the right in the tree. And in the newer formulation of minimalism, trees are non-planar. This kind of notation for which is equivalent to writing trees, but it's equivalent to write them as non-planar trees. So you can draw them as trees in the plane, but you should really think of this as being freely hanging with all the possible permutations that maintain the same abstract tree structure, but not the same planar structure allowed. So I will come back to discuss this later, but I want to mention that in this formulation that I'm discussing here, this older formulation that I'm discussing here, everything is happening in planar trees, and this is not the case in the more recent one. So in this setting of stable computational minimalism, you have this type of chains of derivations for forming a structure in a minimalist grammar. In this case, you have this movement that comes from the WH movement and comes from building a question type sentence. Right, you start out by having this type of matches, with where you have labels that can be met with external merge. So you have a certain number of external merge matching. And then you have the movement part that is called by the other kind of label feature checking and label matching operation. So, as I mentioned, there is this result that formally shows that these minimalist grammars are actually equivalent to multiple context-free grammars. In terms of generative power, as I said, not in terms of computational complexity, but in terms of generative power. And so the main idea is like how you transform a derivation that is described in terms of these merge operations in a form that is describable in terms of multiple context-free grammar. So you have to account for things like these identifying substructures inside the larger structure with this kind of label feature matching conditions, and use those to prescribe certain kind of production rules in the context-free, multiple context-free sense that will correspond to the merge and move operations. So, for example, if you have a certain structure with certain labeled substructure, you can assemble this information about the structure together as a string as a vector of different substructures. It's the full structure and its different substructures. And this vector would correspond to the vector of context-free pieces that you use to form multiple context-free grammars. And then, the corresponding operation. So here's the same example. So just reformulated in terms of these vectors of descriptions of structures and substructures. And it will become a series of production rules on these strings, on these vectors, and the resulting string at the end, will be something that can be described in terms of strings produced by a multiple context-free grammar. Okay, so the next step in view of what we will be discussing later about the new formulation of merge and minimalism is the fact that you want to try to interpret this merge and move as two aspects of a same kind of merge operation. So this transitions to the more recent notation that thinks of this external and internal merge. And so the external merge again is matching this type of labeled features and combining tree with a certain rule on where the direction of the head points. And internal merge in the same way is viewed as an external merge applied to the extraction of a substructure when you have this other kind of feature matching labels, and where what you extract here is the maximal projection of the substructure, and on this side you take the overall structure from which you are extracting, and you replace the labeled substructure with the empty subtree. So you're removing the subtree. Okay. So let me just say one thing about these heads indication, because in this formulation of minimalism, you have this additional data of this that labels the internal vertices, not the leaves, but the internal vertices of the tree, and it keeps track of where the head of the substructures goes. So, for example, here, the label on this last subtree here is saying that if I take out this substructure and just look at this substructure, the head of this substructure is the leaf that's labeled 8. If I go up here one step and I look at this whole substructure that includes the leaves 7, 8, and 9, then the head here goes into this subtree, and then it actually goes again to 8. So this head projects up to this substructure, and if you see, it actually projects all the way up to the root of the tree. So this is actually the head of the entire structure, and its maximum projection is up here at the root. If I, for example, take this substructure here with the leaf 5 and 6, then the leaf 5 is the head, but this head does not project further. So this is also its maximal projection, and so on. Okay, so these are the rules for how the head functions, and later on we will actually abstract these rules and define what a head function more abstractly is, and this would be essentially the defining rules. So in terms of notation, right, you have the kind of labelings that are involved in these minimalist grammars are these ones that keep track of the head on the internal vertices, and this kind of syntactic feature labels, and the selector, licensor, licensee, which later on we will switch to using symbols that are not already used for some standard other use of mathematical symbols, just to avoid notational confusion, but this will sing. And if a label that's attached to an entire tree is actually the label that's carried by the head of that entire structure. So that again, the notation about this. So I spent a little more time on this because later on I will have to return to this and make a direct comparison with the newer version of minimalism. So these are, again, examples of derivations in this carried out in computational minimalism, where you have, you match things that have matching kind of labels through external merge or merging several steps, and you use the other kind of matching features to identify where movement can be applied and what type of movement you obtain. So the idea of reducing everything to, instead of looking at these production rules of formal languages, I mean, we have seen in this previous overview that very quick overview that I've done of earlier phases of generative grammar, that there's always some kind of underlying formal language. Either first either one can think of it in terms of context-free grammars, which were shown not to be sufficient, or classes of mildly context-sensitive grammars, or in terms of transformational grammar, where you have like a core context-free grammar, and then you have transformation rules on top of that. But somehow, these core production rules of a formal language are something that is usually, very complicated to describe. Even for a kind of simple aspects of syntax of an actual natural language, the production rule in the science of formal languages can be quite complicated. And the idea of the main step in going in the minimalism formulation was that all of that is reduced to simply these two kind of operation merge and move that will eventually get unified into a single type of operation or merge. And one of the in a sense, justification for why passing to this much simpler type of formulation is desirable, apart from the fact in general that the formalism that is based on fewer assumptions is always preferable in terms of the theoretical science. I mean, it's always if you can Valencia non sum multiplicanda preter necessitatem. So you shouldn't have more complicated rules if you can have simpler ones. That's a very general principle in science. But there are also compelling reasons for things that need to be justified. The language is in evolutionary terms is a fairly recent and phenomenon that evolved quickly on an evolutionary scale. And so in order for something like that to happen, this shouldn't be the case that an enormous number of different things have to happen at the same time and have to fall into place into exactly the right type of structure. And that would be difficult to justify. But if there is the computational the main computational mechanism that is lies behind the possibility of constructing syntax of languages boils down to a very simple basic operations, then you just have to justify the emergence of that, right? And so there is this recent book by Berwick and Chomsky, which sort of trying to give the evolutionary argument behind the structure of minimalism in syntax, and why this the proposal that this will be then a single evolutionary change leading to the main structure of human languages. And well, I will come back to this later, especially later on in this class, I will discuss the problem of modeling the interface between syntax and semantics. And there, you have to, if one assumes this fact that it's a core computational mechanism of syntax that is responsible for the main evolutionary step in the acquiring languages, then everything else that happens has to piggyback on structures that already existed in evolutionary terms for other reasons, and that would be the guiding principle for a kind of minimalistic model of syntactic places that I will be discussing later on. Okay, so now this concludes the general overview about the historical development of generative linguistics up to before what I will be talking about, which is what happens in these last 10 years, and especially what happens in this last year. But before I do that, before I start to introduce the recent theory, I want to discuss one last topic that is still related to the formal languages perspective, which is the incorporation of data of probabilities in formal languages. And this will not play a role for a long time in the rest of this class, but I will have to return to this near the end of the class, when I'm going to have to give some kind of discussion of comparative discussion of what the theory of language, where the theory of language stands from this point of view of generative linguistics, and what is happening nowadays in simulating languages in machines, in particular what large language models are doing and are computing. And there, because this machine side story is intrinsically probabilistic as a construction, then I will have to return to what is the role of probabilities. And so because of that, because I will need that later on, I want to also give a bit of a historical perspective on the role of probabilities in linguistics and in generative model like formal languages. So that's the thing that I am going to discuss next. And get on to. Okay. Sorry, it's on the wrong set of slides. This would be the following one. Yes, here we are. Okay, yes, there we are. Okay, so the premise for this discussion is that the computational mechanism behind syntax is actually a completely deterministic computational mechanism. So there is nothing probabilistic about it. We will be discussing this for a long time in more detail. This can be modeled as a completely deterministic way. So on the other hand, a lot of applications in computational linguistics that have to do earlier on with various forms of natural language processing, more recently in connection with deep networks, transformers, large language models, are intrinsically and fundamentally probabilistic by construction. This I will discuss later on in this class, is because these are going back to formulations of a theory of language that predate generative linguistics, and that are based on a kind of distributional probabilistic, on the idea of distributional probabilistic data. And however, there is a point here that is a bit subtle, to discuss, in the sense that the fact that one does have a known probabilistic model of a computational process or a mathematical entity does not a priori mean that probabilistic methods cannot provide useful information about it. I will come back to discuss this later in this either this next time. And but I mean, a striking example of something like that happens in mathematics. There's a whole branch of mathematics that is called probabilistic number theory. And there's nothing less probabilistic than, for example, whether something is a prime number or not. The set of prime numbers is one of the most deterministic thing in the world that you can think about. Either one number divides another, or it doesn't divide No, there's no probability about it. It's not that it divides it 30% of the time. But nonetheless, there are interesting theorems and results that can be proved about a completely deterministic set. It's a completely deterministic sets in number theory using probabilistic method. And in many cases, I will discuss this more, but in many cases, the set of prime numbers is valuable, simulated or modeled by random variables and and independent random variables. They're not, but they for many mathematical purposes they behave as if they were. Okay, so I'm saying this because that there's some contentious issue, the use of probabilistic methods in linguistics, and the point is that it shouldn't maybe be considered, like that. So using probabilistic method doesn't necessarily mean that the process one is describing is probabilistic. It means that sometimes, mathematical tools from probability can be applied to, discuss things that are not probabilistic. That's my, take on this. But let me first, go through some of the history of the role of probabilities in, first of all, in the context of formal languages. That was the historical development of generative linguistics. So, well, the simplest kind of thing, that more naive and simplest kind of thing that one can do is, if you're looking at strings on a given alphabet, is to assign probabilities to the letters of the alphabet. And so this means that you're forming strings in this alphabet by drawing each successive letter randomly from a certain probability distribution. So each letter is an independent, identically distributed independent random variable, and it's oblivious to what comes before, and every time it's drawn from the same probability. And so these are the Bernoulli measures. And if you look at the set of all strings that start with a given fixed string and then continue in whichever other way, these are the cylinder sets. And they generate a topology on the set of all infinite strings that topologizes this set as a Cantor set. And the Bernoulli measure, so where you assign probabilities to the letters of the alphabet, induces a probability measure on this topological space, where the generating sets of the topology, the cylinder set, have probability, which is just the product of the probabilities assigned to the letters of the string that determines the initial string that determines the cylinder set. And so this is like the most random kind of the most unstructured. I mean, the most random doesn't mean much, but the most unstructured kind of way of inducing probabilities on strings of text. A slightly more structured way, is to also assign probabilities to the letters of the alphabet, but also assign transition matrices that take into account successive pairs of successive letters in a string. And so this set of transition matrices is supposed to form a stochastic matrix. And as such, this is going to have a Perron-Frobenius eigenvector, which is what you should use as your probability distribution on the alphabet. And again, this induces a measure on the resulting Cantor set, which assigns to the cylinder sets a measure which is now given by the stochastic matrix, the entries of the stochastic matrix for each pair of successive letters and the initial distribution. So now this means that you're no longer completely randomly, independently selecting the successive letters of your strings, but you are assigning them according to a Markov chain, which now remembers where you were at the previous letter and assign the probability of the next one depending on that, and takes into account successive pairs. So this means that the assignments of letters follows a certain kind of Markov chain, which you can think of it as a directed graph with corresponding probabilities along the edges, and with the different possible letters of the alphabet as the different states where you can move from and to at each step. And in particular, in these cases, this Markov measure will have a certain support, which are the pairs of successive letters that are allowed to occur. So the outside of the support, it will have probability 0 that you have a certain successive pair of letters. And both the Bernoulli and the Markov measure have an invariance property. They are shift invariant. If you have a sequence and you shift it, it's the probability is invariant. And this shift on infinite sequences in a given alphabet is a very well-known model for a lot of interesting dynamical systems, the sort of symbolic dynamics modeling of various dynamical systems. And there's an interesting bit of history here that actually Markov chains were introduced in the early 20th century by Markov, exactly as a way of studying text in language. So the actual original motivation for introducing Markov chains or Markov models was exactly analyzing the statistics of occurrences of words in text. And one of the original application was the analysis of the Eugenio Negin in Russian literature on the basis of this kind of statistical analysis. Of course, when you talk about probabilities, the natural measures associated to probabilities are entropy measures. And again, the old development of information, entropies and information in the 1940s, Shannon entropy, it goes back to this main text, Shannon and Weaver on the mathematical theory of communication. And it's a way of analyzing your encoding and decoding of signals in strings in a certain alphabet, and know how effective your encoding is and in distinguishing the carrying information. And so the entropy in the Shannon sense measure the amount of uncertainty that is associated to a prediction of a result of an experiment, or equivalently, the amount of information that one gains from performing this experiment. If you have a Bernoulli measure, all you can extract as amount of information is whether the probabilities that are assigned to the different letters of the alphabet are different, and by how much. If all the probabilities is concentrated in a single letter, that there's no ambiguity, there's no uncertainty. All the strings will have to just be constant strings in a given character and in a given letter. Whereas if the probability is uniform across letters, is the case where you have the most uncertainty and where this entropy is maximized. And for a Markov measure, there is also a corresponding entropy, which actually agrees with the Kolmogorov-Sinai entropy of the corresponding dynamical system of the underlying Markov chain as a dynamical system. And you have other measurements that keep track of information. For example, you can compare probability distributions with the corresponding Kullback-Leibler divergence in information, which is basically measurement and measuring if you have you have events that are drawn according to one probability distribution, but you are trying to model them with a different one. What is the gap of information between these two? That's one way of thinking about what the relative entropy Kuiper-Gleiber divergence is measuring. And it's not a distance of probability distribution, but it's first order approximation is the Fisher information metric that is an actual distance of probability distribution. So it's something that's kind of in some sense close to being a distance, although it doesn't itself satisfy the properties of a distance. And similarly, you have cross entropies between two probability distributions. And in a sense, it's measured like the expected message length per datum when you're measuring with respect to a wrong distribution with respect to the ones that is really the data are really following. Okay, so you can think of this kind of cross entropies and as being a sort of model evaluator. If you are modeling a certain, according to a certain probability distribution, but you don't know what the actual real one is, and this gap of the cross entropy is sort of telling you how good your model is or not. And if you have a formal language, the outcome of a formal languages are strings. If a formal language is a certain subset on the set of all strings in a given alphabet, all possible strings in a given alphabet. And so you can look at all the words in the language that have a certain length in the alphabet, and you can look, for example, at asymptotic behavior of per word entropy when the length of your strings grows, and this is a certain invariant associated to a language in this sense, a formal language in this sense. And again, you can evaluate the cross entropy with respect to different model probability distribution and an actual underlying probability distribution in this asymptotic sense. There's this kind of asymptotic behavior of the number of words in a language. You can construct a corresponding generating functions. The generating functions associated to formal languages have very interesting properties. You can get interesting information about, for example, for context-free languages, you can get interesting information about the context-free grammars that can generate the language on the basis of corresponding generating functions and the behavior. There's famous results of Chomsky-Schutzer-Berger about that. So there's another way of thinking about an entropy that is associated to a formal language, which has to do with the radius of convergence of the corresponding generating function, and the logarithm of the radius of convergence, and that also gives you information about the structure of different formal languages. So these are some aspects of how probabilistic information can be used in the context of formal languages. And one of the early probabilistic models is the N-grams of Shannon, and this again based on looking at co-occurrences of pairs of words or multiple combinations of words in text, and probabilities that are really deduced from frequencies of occurrences in a given corpus of text. And of course, it's immediately obvious that there's a problem, right? With this idea, namely, that you can have perfectly grammatical combinations that are just unlikely to happen, to occur frequently, but are perfectly viable as from the grammatical perspective, and this would be suppressed in a probabilistic model. And Also, there's very sparse and very infrequent data. Typically, I mean, if it's if you try to look at this as the structure that involves several words, so the probabilities in a corpus become astronomically small very quickly. So one way to kind of compensate for this problem in this N-gram type probabilistic model was to smooth out the probabilities in the sense that for example, you can have that the probabilities of occurrence for sorry, this is in the wrong order, 2n minus 1, but okay. If you list the co-occurrences for more than, this could be very small, but you can combine them with the individual occurrences probability and the pair occurrences probabilities, and have parameters that take care of this smoothing out of probabilities. And so this means that the actual N-gram models should be thought more as hidden Markov models. So the first step, right, is to consider a kind of Markov chain where you look at all these occurrences. For example, if you're a trigram case, you look at each word or letter, depending what your units are. But anyway, it's J and the two previous ones, and you look at all of these together, and you want some kind of probabilities of transition. So given the previous two occurrences, the probability of transitioning to the next one. And what this actually means, right, would be that you have this was this is the end one that you want to transition to the end element in the sequence. This would be the end minus first, and this would be the end minus second. So it means that you want to go from a combination of A, B to a combination of B, C. This would be the transition here. So you kind of think of it like this, right? You have a combination of A, you can transition to the remain itself by adding a new A, or transition to AB by adding a new B, and transition to BA. So this would be the corresponding transition probabilities for all of these possibilities. And this would be, your corresponding Markov chain. Then, as I said, the next step is to actually smooth out these probabilities that involve pairs, so that you compensate for the fact that a lot of them become extremely small. And so this now introduces new parameters here that are the smoothing of probabilities, and you're now considering probabilities both of single occurrences and both of one occurrence given the previous one, and of one of the next occurrence given the previous two. And these are new parameters are considered your hidden variables of your hidden Markov chain. So they are states that don't have any output symbol. So you get something that now is a bit more elaborate as your Markov model. Now you have these assignments of these smoothing of probabilities that are part of the model, and then you have the corresponding transition. So the transition from, say, a B to BA is a combination of these possible transitions and so on. Okay, so the kind of very early discussions of this model in the 1940s, Shannon, who was, for example, trying to create successively better approximation of something that would look like an English text. So of course, if you just use a Bernoulli distribution and just randomly assign letters where all you know is that the occurrences, the frequency of occurrences of each letter is the same as the frequencies in English, you will get something that doesn't look at all like, sorry, well, first of all, if it's a uniform Bernoulli distribution, then you get something that doesn't look at all like a language, in any sense. If it's a Bernoulli distribution that is based on the actual frequencies of letters in English, you still get something that doesn't look like a language at all. But at least the number. So E is a letters that's very frequently occurring in English. Other letters are very rare, and at least the number, it's already something that in some way, sort of vague sense, looks closer than this uniform Bernoulli distribution, right, to something that would resemble an English text. But now, if you look at the distribution of two consecutive letters, and now you consider a diagram model, you start to get something that, again, does not look like English text, but it sort of has more of a feel of something that might look like English text. And finally, with the trigram model, you have things that, again, are not English words, but in sense they could be. I mean, they're something that, if you syllable, well, they're not, they're not, but you wouldn't be surprised if somebody would tell you that they actually are. Of course, you can do the same with entire words as your building blocks rather than single letters. And try to look like, how much these look like sentences. And again, there's from just as probabilities of single words and probabilities of diagram probabilities, you get something that's more resembling a letter. Okay, so this kind of things is kind of games about probabilities and text and information, Shannon information, and associated to them. They're, of course, very dependent on how one describes, text. There are one of the, famous Macy conferences of cybernetics in the early 50s, where people were also discussing this type of entropies and probabilities and in the strings of text and languages. There was this example, provided by a linguist. And it just shows how, saying that what is the Shannon entropy of a text is highly dependent on what you mean by a text. This is a short story in Mandarin, and the thing is that the written text, I mean, the story doesn't make much of a sense, but the thing is that the written text has a lot more information than if you just think of it as a spoken text, where the only information you're left with are the tones, because all the other things is all the same. So she with different tones. So and of course this example works because languages like Mandarin has a very many to one function from the written characters to the pronunciation. And so you can get this enormous drop in Shannon entropy by going from one to the other. But here's an example that shows that there's something that you can do, with a language like English as well. It's not something that depends on the particular features of Mandarin. So the interesting example here is that you can form an arbitrarily long sentence in English consisting solely of the word buffalo. The reason for this is that the word buffalo can have different meanings in English. There's a buffalo as a verb, buffalo as in bullying someone. And there's a buffalo as a kind of bison, an animal. And there's a city of Buffalo, so there are buffaloes that are from the city of Buffalo, and they bully someone or bully other buffaloes, for example. And so you can form sentences that are entirely grammatical, entirely syntactically correct. They have a good syntactic parsing where all the lexical items consist of the word buffalo. Of course, the several observations that one can draw from this example. One, of course, is that when we talk about lexical items, we talk about lexical items together with syntactic features that we tell what role that lexical item is playing in a sentence. So, for example, there's a buffalo verb, there's a buffalo noun, there's right in this case. And also, the main point in this example is that the information, where is the information? The information is not in the string of text, right? The information that language carries is not in the string of text, because in this example, the string of text has strictly Shannon information 0. And but the information is actually in the structure, in the structure as the syntactic tree, and that is the part where the Shannon information is non-zero. So, for example, this is the parse tree of one of these buffalo sentences. So in this case, there are bisons from the city of Buffalo, that bison from the city of Buffalo bully and themselves bully bisons from the city of Buffalo. Okay. So one additional remark about the buffaloes. It's a very simple exercise that I invite anyone to carry out on their own to show that give a simple mathematical argument to prove that indeed you can form arbitrarily long sentences, all of them with correct syntactic parsing consisting only of the word buffalo. There are some linguists out there, distinguished linguists out there, who keep making the claim that it's not true that sentences produced by a language are a countable set. Of course, you will never actually, in real life encounter, sentences that are, longer than a reasonable amount. But the point is that it's exactly like these examples that I was mentioning of recursion. So you can help someone, help someone, help someone, or you can get someone, get someone, get someone, and you can, and so on. I mean, there are many of these examples, including the ones that give rise to various kind of cross-series dependencies, depending on the language or other kind of series. The point of that is not that it is realistic to run into an actual sentence, that you speak or that you read or that you write, where there is 10,000 of these iterations. That will not happen. The point is that your brain immediately acknowledges and recognizes that these recursions can continue and that will continue to be syntactically viable, even though you will not actively, practically use them. Right? Not only your brain immediately recognizes that, but you can also show it in a logical argument using the induction principle. I mean, some linguists are extremely confused by what the induction proof means. Unfortunately, I've now happened to see papers where something completely nonsensical was said about what the induction principle was, and tried to criticize generative grammar, and tried to find something to criticize generative grammar. So, the result is that some people, write 30 pages long papers to, announce to the whole world that they don't understand the induction principle. This is highly embarrassing. But, the point of this is that it's an uncontroversial fact that there's a countable set of sentences that are grammatical, and this doesn't, even though you don't necessarily run into them in life. It's like the set of prime numbers is a countable set, and you can prove that it is. In real life, you will encounter prime numbers that maybe are very large if you're working in cryptography, but they still are within some finite limit. But this doesn't make the set of prime numbers finite in any sense, right? Okay, so I know why one needs to clarify these things, but if you look around, you will discover surprisingly that they do need to be clarified. Okay, so next time I'm gonna continue finish discussing these probabilistic methods in the theory of formal languages. And because of this fact, right, that clearly the information is contained in the parsing structure in the trees, not in the strings of words. The idea is that one shouldn't try to put probabilities on the string of words like these Bernoulli and Markov cases, which are rather uninformative in the end. But one can try to if one wants to use probabilistic methods to argue things about non-probabilistic computational structures like language, the probabilities has to at least go in the right places. So that's there's a way of making probabilistic context-free grammars, which has been used. Many is used in has been used in natural language processes. It's not the focus of the current version of machine modeled languages, which I will come back to discuss later. But okay, next time I will finish this quickly, this overview of historical overview of probabilistic methods, and then I will continue on with our main focus, which is the merge model of linguistics in the more modern formulation of the past 10 years. Okay.